Hello and welcome to this low-level JavaScript video where today we're going to be building a priority queue. Now, a priority queue is a data structure which is a queue which is kind of like a stack or something, right? It's got like operations to put stuff into the queue, it's got operations to take them out of the queue. And the special property is that the things we put in the queue will have some sort of intrinsic priority associated with them, and we provide the queue some mechanism for determining the sort of relative priority of different values. Right? You can put anything in the queue as long as you have some way of determining its priority. And what will happen is that we'll put items into the queue, and whenever we go to take an item out of the queue, we will get the one which is the highest priority for us by whichever metric we have defined highest priority. Now, the simple example, and probably the one that we'll work with for the majority of this video, is just like, let's say our priority queue is made up of integers and or just numbers in general, right? And we push a number into it, and we say that, for instance, a lower number has higher priority than a higher number, right? Just to show that you can do that kind of thing as well. You can absolutely make it so the higher numbers have the priority over lower numbers, and you could absolutely do something like putting a complex object into the queue as long as it has some sort of deterministic way of determining its priority relative to other items. So yeah, normally on this channel I don't do necessarily these kind of videos, which is just like looking at a single data structure. And the reason I'm doing it today is because, like, in some upcoming videos I want to be exploring some topics in compression, and the priority queue turns out to be a really useful data structure for some compression algorithms. Not strictly necessary, but kind of a useful thing, and I think it's going to be fun to dive in. There's a few interesting points that I find personally quite fascinating to do with how we'll actually store this, and the nature of this data structure, but also the way it's stored, and how that there's a sort of conceptual gap there, which I think is interesting and kind of beautiful in a way. And if you've arrived here from like searching YouTube about priority queues, well, welcome for one. You are going to actually see a proper implementation. Like, we're actually going to write code here. I know that a lot of these kind of data structures kind of videos on YouTube, they often just someone sitting on a whiteboard drawing things, which is fine. But sometimes it's good to also see how to write code as well. So that's what we're going to do here. And it kind of won't really matter which language you're coming from. These principles are going to apply no matter what, as long as you have like the basic sort of primitives in the language to do like the sort of basic operations we're going to need to do, which are to do with things like arrays. If your language is going to be able to support like dynamically changing the size of an array, for instance, then you're going to be fine, which you can do in pretty much every language. Even in the immutable ones, right, you would just create a new array, but that's neither here nor there. Let's actually dive in and take a look, just try and get a conceptual idea of how this is going to look, then go into the code, and we'll kind of whip back and forth between like trying to visualize what we're trying to do and writing the code, and hopefully we'll get to something really cool. So let's go. Alright, so here we are. We're in just like, I guess, my virtual whiteboard, so you know, like I guess you do need some level of it just for the visualization part. What I'm going to do here is make a little kind of memory representation, and like this is kind of our conceptual thing. And maybe in the beginning, oh okay, it's like hard coded as a square. Fine. What I want to show here is like a simple idea first, like so this is kind of our priority queue, and let's say we're putting numbers into it, right? You'll have to excuse me if my voice gets a little bit scratchy. It has been a little bit scratchy in the last couple of days, so hopefully it lasts out. Let's imagine It's going to be really big font. It's really funny. Let's say that's something a little bit more sane. It's kind of somehow really badly aligned text. I'm not sure exactly what's going on with that, but alright, good enough? Yeah, alright. So let's say we have this priority queue, which is this, like kind of this thing, and we can shove everything that we want in there. So let's say we've got a bundle of values here, and we're going to put them all in our priority queue. So let's say we put 10 in first. Well, it's the only thing, so it's kind of like when we go to pull something off, it's the highest priority item just because there's only one. And then let's say we throw 1 in, and well, 1 is now the highest priority item. We sort of, doesn't really matter what happens with the rest of them, but 1 is kind of taking that place. And then let's say we're putting 5 in. Well, 5 is not the highest priority, so it goes in this black box area somewhere. Maybe another 5 goes in too. And as we take an item out, somehow through some mechanism, the next highest priority item is gonna kind of appear here, and the next time we want to go and grab something off it, like we're going to get the right one. And again, if we pulled 5 off, like kind of magically, the next one would appear here, and we could pull that off, and then we get 10, and eventually, you know, it's empty and we can't pull items off it anymore in a meaningful way. So how this actually works, and kind of the reason that this is just more than, for example, just pushing an item into an array and then sorting it, which would be a technically correct implementation of a priority queue. The actual thing that makes it important is the speed of operations. So, like, if you imagine a sorted array, and you imagine the priority queue, well, pulling an item off is a constant time thing. We have it ready. That's kind of what we're saying. In a sorted array, it's just going to be the first element in the array. We know how to grab that. It's a kind of constant time operation. We don't need to worry about that. What you need to think about is that when we go to insert an item into the queue, well, in that moment, we then need to sort the array again. And so you're kind of, yeah, whatever, let's say we're doing, you know, the most basic sorting algorithm, and, you know, we get this, like, we have to go through each item in order to insert this this new value. Kind of, we need to resort. In the priority queue, you don't have to go through every item, you only have to go through log n items. So that's a big improvement. And if you have to use this queue to store a lot of things, and most critically, if you have to take things out and put them in quite often, which in the compression side of things, that's something we'll have to do as part of the algorithm. We're going to have to use a priority queue where we pull items off and push items into the queue a lot. That can make a huge difference, especially if the number of items is really large. So that's the crucial thing, right? It does this job really well, and that's its main thing. I'm sure that there are many things you can think of. Once you know this data structure, you can start to think of places where it's applicable. Like, yeah, when you have stuff that needs to be done in priority and you want the ability to pop it off. In event-driven kind of systems, this is a useful thing. When I say event-driven, I mean like maybe UI event-driven, like maybe it is also a useful pattern in kind of like the broader sense of event-driven systems, but I wouldn't know about that. So yeah, so that's kind of the idea. And the way in which we're going to do it is that this is actually going to be kind of a tree representation. So we're going to have, like, in this case, we're going to have one at the root of our tree, then we're going to have these two 5s, and then we're going to have the 10 down here, and it's going to connect up kind of like in this way. Let's make that a straight line, and so it's something like this. And then if we came to insert a new item, let's say we had 44, well, we're going to throw that down here. And and then we're gonna kind of go kind of conceptually from the tree perspective. We're gonna go from the top, like in this zigzag where we go top to bottom and left to right. So we're inserting items like in that kind of way. So first here, then here, then here, then here, here. The left item of this node, the right item of this node, and then going down to the next level. So that's kind of like conceptually how the tree is going to look. And the really, really interesting sort of mechanical part that comes into this is, like, let's say we come with a new item, and our new item is 0, right? Which is going to be an intrinsically higher priority item than 1. The mechanism for this is that we would put it down here in the wrong place. And by the way, I'm not going to go deeply into this, because if you want to go into the real deep theory, there are a lot of resources for it. Just go and watch one of the whiteboard videos and you'll see all the details, or just read Wikipedia article or something. But this is obviously a binary tree, and it's a heap, and that means that it needs to satisfy a bunch of constraints and invariants in order to be a valid heap, right? It is always be a valid binary tree as long as it has 2 nodes. Even within binary trees, you can have like certain kind of invariants for the different types of binary trees that you're dealing with. But in this case, this is now kind of an invalid heap. So in order to get it to a valid state, we need to get this 0 somehow up here to the root, and we need to get the 1 in the right place relative to that. And so the way we would do that is that this, when we go to insert into this, like, kind of the deepest part of the tree, as it were, thinking of this going top to bottom, left to right sort of way of thinking of things, we're going to take this node and we're going to look at its parent, and we're going to see if we need to swap them around. And like, we may well need to swap them around, right? Like if this one has a higher priority, so we swap them around, and then we're in kind of this state. And then we need to do the same thing again with this node and its parent. So in this case, again, we need to swap these two. So so the one goes down here. It's really annoying to do these arrows all the time, but that's fine. So then we end up in this situation, and now we're in a valid state. And what you'll notice, right, is that this isn't like a fully ordered tree or something, right? This is not an ordered binary tree in that following that schema. Is what you would call a partially ordered binary tree. And that is kind of the key to the speed of the thing, right? We don't actually, like, when we're dealing with the number of operations that we need to do anytime we like remove or insert something, it's to do with the number of levels of the tree in the worst case, and not the number of elements in the system as a whole. And that's why it's this log n, right? You can sort of go and look at the relationship of these n and log n and all of that kind of things. But this is kind of the relation there. It's to do with like the height of the tree more than the number of elements themselves. So that's kind of it. Well, it's not it, because if we were to take this 0 off, like, obviously we need to put a new node in, right? So let's take that off. That's over here. We've got that value now. And the way in which we kind of resolve this like sort of broken tree now is that we say we take the deepest node in the tree and we put it as the root node. So we do something like this. And again, that can potentially leave us in this broken state. So we need to think about how to correct for it. And the way we do that is we look at our 2 children of the root node, and we see if we need to swap with any of those. And in this case, we would need to swap with the 1. And so we do that. And yeah, then we end up in this situation, and we're actually kind of fixed at that point. And if we had further children on this side, we would do the same operation again. We would just see, does this one need to swap with either of its children? Now, it doesn't happen to have any, but if it did, and the conditions weren't correct, we would just perform a swap there. And we do that until we reach the bottom of the tree. So you can see that in one situation, we're going from bottom to top. That's an insertion. And when we do a removal, we're basically in a situation where we go from top to bottom. and it's always coming from the two extremities of the tree, right, in order to fix, and it's always going to be the same kind of worst case number of operations. So that is the conceptual side. And the one of the interesting things that we're going to be doing here, and that if you haven't done tons of this kind of stuff, I think will be pretty interesting, is that we're going to be representing this tree in flat memory, right? So in an array rather than in a linked tree structure. And that's pretty cool, right? There's some interesting relationships that go on there, and I think yeah, you might find that kind of you might find that inspiring if you haven't done a lot of it before. So let's actually switch over. I need to just open a little window here on my display so that I can move things around. But let's switch over to the code now and actually start writing the code. So off the bat, I'm going to export a class, which I'm going to call priority queue. And this class is going to be generic. Now, if you are working in a language with generics, then this is fine. If you're not working in a language with generics, then and it's like a loosely typed programming language, then no worries, right? The T just means it can basically be any value. The kind of implicit constraint there is that it can be any value, but all of the values you put in should be the same. Otherwise, you can't meaningfully compare them. But we're just saying that we don't care what the value is itself. It can be anything, but like once you've kind of locked it into that type, it's done. All right. So another thing we're going to need is a way to compare these things for priority. So we need a function, and it's the same kind of function you would plug into a sorting algorithm. So let's make I'm going to export all my types here. So if this were kind of a library, the user would be able to use those types in their own abstractions. So let's call this a comparator function. Don't know if that's how it's spelled correctly. This function is obviously also generic because the priority queue is generic. The way you compare the items is generic. Basically, the way this will work is we'll get a function with two inputs, A and B, and that has to return a number, and that number will indicate whether a kind of ordering operation between these two elements. So either like a negative value will indicate that kind of A comes before B, let's say. A 0 value will indicate that that the two values are equal, that we don't need to do anything, and a greater, like a positive value will signify that B is the larger value. I may have gotten myself mixed up there in the things, and we'll actually test it empirically in the console anyway, but that is the comparator function. And also, let's just make a quick type here for the parameters of this, like what we pass in to this function, like a name set of parameters, like an object. It's also going to be generic because it's generic over the same type as the comparator function and like the things that go inside. So it's also generic, and then it's an object with a comparator function. A comparator function, right? It's got one of those. It's that type. And let's say it can have also initial values, and they're optional. And that's just going to be an array of T, right? An array of those things. And we're going to put those in the queue somehow. So, internal members, I'm going to write everything as public in the beginning, and then at the end of the video, we will close everything up and make the interfaces private and only expose what we need. But for testing purposes, it's usually useful to do that slightly later stage so that you can introspect things easily. Okay, so values. That's going to hold the fundamental values of our system. So we'll make that also an array of T. And I'm going to set that to be an empty array in the beginning. Yeah, that's pretty interesting. The emptiness, well, we'll get to that anyway. But yeah, so that's actually going to represent our tree. Then we need to keep the comparator function internally as well, so it's just a little bit boilerplatey here to kind of mention these things over and over again. And then we get our constructor. That's going to take params, which are priority queue params of t, and then we'll say this dot comparator function equals params dot comparator function, and if we have params dot initial values, if we have an array there, then what we'll actually do is call this dot insert with the value, and we're going to need to do that for each of the values. So let's do params dot initial values dot for each value, and we'll call insert with the value. Obviously we haven't defined insert, so let's just stub that out so we're not like creating a syntax error. Insert is a method that takes a value of t and does something with it. Does some insertion. We'll get to that. The other operation, like the two operations we need to support, are insert and remove. So remove, when we do this, this is going to be returning either a t or null, or some kind of optional signifying value, right? If you want to go off and write this yourself and you want to write it with like optionals or like the maybe type, yeah, you can certainly do that, and it's actually probably a good thing to do. I'm going to write it with null as the empty signifying value, but yeah, if you have to think, like if you imagine that some of your users might want to, you know, use null as like a valid value, which is kind of weird because you can't compare it, but yeah, if you imagine that that might be a situation that you users want to do, then certainly do that. What I'm going to do is I'm just going to make a type, and this type is going to do nothing within the TypeScript type system, at least, because it's just the way that TypeScript works internally. But this is a type where t can be, where we sort of say that it's optional t, where t is either a valid value of t, like any type, number, string, whatever, or it's null. And so we're saying that this returns an optional of t. Right now it doesn't return anything. We can fix that, say return null. But fundamentally this actually just will like in some situations this will even just tell us like this function just returns t, right? Returns t or null, but that's everything. It's not like that in every language, so just keep your eyes out. Yeah, so these are our two operations. They sometimes get different names. So sometimes that's called, like, insert is called Q and remove is called DQ. I'm going to go with insert and remove because I think they're just like clear names. They read nicely even if you don't necessarily understand like that you're working with a priority queue implementation. It's still pretty straightforward what that's doing. Yeah, and now we have to like basically write these functions. So when we go to insert something, the first thing we're going to do here is we're going to see if we have enough space in the array. And I actually missed one thing that we need to have, and that is a length property, which will start at 0. And yeah, there's a reason that I'm like values has a length property, right? Because it's an array. There's a reason I'm keeping a separate length property. And that is that when we remove items from the array, I'm not going to resize the array to be smaller. I'm going to just only ever expand the size of the array. And then what that means is that we can reuse old slots of the array as we go. So yeah, the first thing we're going to do is we're going to see if we have enough space for the item. So the way we check that is we say if this dot values dot length, if that's greater than this dot length, that means like this is the capacity that we have, and this is like how many things we actually have. So if we have a more capacity than we do length, like the number of items that we have, then we can just insert this thing without resizing. And what I'm going to do is kind of switch this around to be if the capacity is less than or equal to the length. If the two lengths are equal, that also means that we've used every slot available to us, and we need to expand the array. And the way I'm going to expand the array is to say that this dot values dot length is going to equal math.max either 1 or the current number of values multiplied by 2. So this is like an exponentially expanding array. This is not necessarily the best way of doing this. You know, you can, I think it's nice, it's concise, you know, but it might not be the best in terms of performance. You know, technically this trick is really just a kind of performance trick. So, you know, whether it's whether it works or not is a different thing. But yeah, basically what we're doing here is we're kind of implicitly expanding the size of the array by writing to the length property. And yeah, we're exponentially increasing. So if we start with 1 element, we're going to double the length to 2. If we have 2, we're going to double it to 4. If we have 4, we're going to double to 8. And then the idea is kind of through that exponential, through that kind of exponential increase, we should like kind of naturally arrive at the right number of elements for our use case by not having to do too many expansions, right? Yeah, there's a kind of there's like a kind of comparison there that you can do to the number of levels in a binary tree also. But yeah, it's for something else. So once we've expanded it, we know that we have enough space for it. And whenever we insert an item into the queue, it goes onto the end of the queue. It becomes the very last item in the array. And remember, this array is going to represent a tree structure. So this dot values, this dot length -1, which is the kind of last position. Sorry, length, because like length is indicating where we should insert basically. Since we start on 0, like the first element should go into the 0th position. So we are going to set that to value. So at the very end of the array, set it to value. Then we can say this dot length ++, right? Because we've increased the length. We could also do the ++ here if we want. Why not? We increase the length of the array, and then we actually need to do this procedure that I mentioned over here, where we see if like the new value that we put in, like we say we put this one in down here, like do we need to like kind of swap up the tree? And this process I have seen it called, and I like to think of it as the bubbling up process. Like this value maybe bubbles up to the top, or it bubbles up to the right point. And this, like if we're taking something off and we pour it down here, then maybe we bubble the value down. So I like to think of those two operations as bubbling up and bubbling down. And just so we get an idea, right? Let's make this. Oh, again, it's gone for this insane size. Let's see if we can do this without it. Yeah, that's a shame. It seems to want to break every time it does that. 0. Okay. Trying to do the world's quickest kind of technical drawings. Everything goes better when you go, you know, super fast. You never make mistakes. Okay, so this is kind of a memory representation, you can imagine, right? This is like the first cell of memory in the second cell. These are our array positions, basically. The way this is stored is like the root node is always at 0, and then you immediately store the next row, and you just go from left to right of each level. So we would take these ones, and then you start again down here going from left to right. So you get 10, 44, and 0 when we're inserting this thing in the before we've done the bubbling. And then yeah, this is going to be our representation of the tree in memory. So with that in mind, we've inserted the thing in, and we know we need to do a bubbling up operation, which we haven't written yet. And then that's actually it. That's kind of our insert, I think I got that right. Insert, increase the value, sort of expand the size of the array. If needed, insert the thing and bubble up. Okay, that's good. Let's just write a stub for bubble up. Now when we come to remove, things are a little bit different, but also not that far removed from this. So the first thing we're going to want to do is to check, like, is the tree empty? Like, is our queue empty? And we can check that really easily with length. If it's 0, then I'm just going to return null. We don't have anything to give back, so just return null. And then you don't have to do this, but I like to make a second kind of special case for the 1, because it doesn't involve any bubbling up. There's nothing to swap elements with after, because we're going to have a 0 length tree after this. So what I like to do is to just kind of get the, at this point, get the node. So this is going to be our our item to come out. I'm just going to call it node, and that's going to be at this dot values 0. It's always at the 0th position, right? That's how this tree works. So what we can do is we can say this dot length is 0, and then I think it's useful to actually set the values position to null as well. I guess we could technically do that outside, but we don't really need to. And then we can just return the node here. Didn't pull in node filter, right? No, good. So yeah, so we do that. We don't need to do any bubbling up in that situation. There's nothing left in the queue afterwards. But in the case that we're going to have some stuff left over, then we need to do this procedure that I've spoken about before, right? Which is we're going to take this one off. And this is kind of not in the right arrangement at the moment, so let's say that's already off. Let's take the 0 off, and then we need to kind of pick a new root node. So we take the deepest node in the tree, which would be this one. We put it up here, and again, keep in mind, right, for us to pick the deepest node in the tree, we just need to take like the deepest node in our array. The same thing effectively. So we end up basically doing this, which is kind of nice. So we take that, we swap it, and then we're going to do the bubble down procedure where we check if we need to swap 44 and 5, which of course we would. We would need to swap 44 and 5. And notice that here, like, you know, we have to make a choice between the left and the right branch. And yeah, we would, well, we'll see how this ends up working out, but we have a way of determining which branch to go down as well. So, all right. So what we actually do is we say this dot values, this dot length -1. That's our last node in the tree. We want to set the value of this. That's going to become the new root node. Then we can actually set this one to be null because there's nothing there anymore. And I forgot, yeah, we set length to 0 here. Yeah, that's fine. I think what we'll do is we'll just say this dot length minus at this point. And then we're going to do the this dot bubble down procedure. And then at the end, we'll return the node because we still need to return what we've got. So we're going to do the bubbling down procedure when we remove stuff. Yeah, so that it's ready for the next one. So we also need to write a stub for bubble down. All right, so now we just need to kind of implement this logic. And well, you've seen it in the graphical form, so it's kind of like conceptually, like as a tree, it makes sense. You're just like looking at either the parent or your children, doing this simple comparison operation. You know, we have this function. The user has to provide us this function from the outside. So really, we just need to, you know, kind of go through, get the parent and child relationships. But how do we kind of do that from having a flat array of values? Like it's kind of yeah, it's kind of an interesting thing there. So Arbitrarily, I'm going to pick Bobble up. I think it's kind of the easier of the two of them as well. So yeah, it's kind of a good one to start with. And we're going to start out with a mutable index. And that index is going to be this.length minus 1. Because when we go to bubble something up, right, we're bubbling up from the deepest node in the tree. And so like that's always in that position. We know that's kind of one of the givens, at least at this point. So yeah, we're going to start there. And you can do this with recursion, right? If you took an index here as a parameter, like say like the node index number, like you could do this with recursion by calling bubble up with an index that will change. But I'm going to write it with a while loop because I think it just makes sense in this case. I mean, it's fine. It's fine. You can also write it with recursion, and maybe that's a nice challenge for you to do. So what we're going to do basically is we need to somehow get the parent of this node, and the way in which we do that, well, let's take a look at the visuals. So let's say we're back in this state. Let's get ourselves into a state that makes sense. So we have 1 at the top. Well, let's just take the 0 out. We have 1 at the top. Then we have the 2 5s, and let's say 44, and well, maybe we'll make like one other thing here, like with a 32, and we'll plug that up there as well. So this is the state of this is our conceptual tree. This is how it's represented in memory. So if, for instance, we start down here at 32, we somehow want to get to this 5, right? Which we know is this 5, because this is 1, this is this 5, and then this is this 5. So, like, kind of naively, we could think, okay, I'm at index 5. If I minus 3, I get to index 2, and that's the right item. I mean, the relationship is not quite that simple, but it's not too far off. So what we do is we take our current index, we subtract 1 from it, and then we divide by 2. And I just want to like double check myself here. Yes, we do have to actually, yeah, do a subtraction operation here. So we, the certainty level. So we're at this index, we subtract 1, then we divide by 2. And then we actually arrive at the right place. And this is integer division, right? So it's like there's going to be rounding involved, and we always round down. So let's like imagine we were here at the 44 node instead, right? So we subtract 1, and then we divide this by 2. Well, that would give us 1.5, but we round down, we end up at 1, and we're on this 5. So that works out. And 10, obviously we can do the same thing. Go down to 2 by subtracting 1, divide by 2, we end up on this one at 1. And you can try it out, we'll see that we do the same thing. So quite a simple operation, but I think that's in a way like really beautiful. It's so simple, but it's just, yeah, this kind of beautiful result. And if you don't think that's beautiful, then well, what can I say? That's up to you. I'm just going to make a little, like, a parent function here. We'll pass it a node index, which is a number. It's going to be a positive integer. We can't express that in TypeScript. But yeah, no one will be able to call this. This will eventually be a private method. So we get the parent. And like I said, right, well, there is obviously a case where you can't have a parent, and that is that you're the root node. So if node index is 0, then I'm actually just going to return a null as a signifier. And otherwise, we can just return node index minus 1, and then we take that whole thing. We need to do divide by 2 and like floor, but we can actually do all of that by doing a right shift by 1, and we're using a logical right shift here, so we don't bring in the same sign bit when we bring it. Like, we're not doing a kind of arithmetic shift. So we do a right shift by 1. That's going to do both a division by 2 for us, because that's kind of what that means conceptually, but it also does the round down operation. So that's enough. That works. Really nice. Really like that. Don't do it in your production code, probably. There's not that many places where you need like divide by a power of 2 and then round down, but this is one of them. All right, we'll get to the children and their relationship in a moment. Yeah, so we've got a way of getting the parent now. So let's say we get the parent index, which is going to be this, the parent. We're passing in the index that we start from, like the deepest node in the tree at the moment. And at this point, we can say, well, one, like if parent index is not null, that's a good start point. And then we run this comparator function. And let's do it like this. We say this.values index as the first argument, and this.values parent as the second argument, parent index. Actually, let's just call it parent for brevity. We're not going to get any name collisions. So that's it. And we need to work out if we need to check minus or positive 0. So let's actually just go into node for a minute. And let's say we get a comparison function AB, and we return A take B, right? That's going to be like the standard sorting function that we can imagine passing in. You could also do B take away A, that's up to you. You can use that to define lower or higher priority, but we'll take this as kind of the baseline. And so let's say if we were to compare, we've got an index down here, and we're determining if we need to swap right now. So let's just think about that. If I have an index like, I insert an index like 0, what I'm going to be saying is compare 0, that's me, with my parent, which is going to be 5. So let's do that. 0 and 5, right? Current index and parent. If we do that, we get a negative number. And obviously the implication here, right, is that we would need to swap these two. We know we need to swap, so we can write this relationship, having, you know, seen how it works, as if this value is less than 0, then we need to do a swap. If it's greater than or equal to 0, we don't need to do a swap, because either it means we're already in the right order, or that the parent and the child have the same priority. Which case you don't need to swap them. So in order to swap, temporary variable, it's pretty straightforward stuff, right? I will choose to put the current index in the temporary variable, though it doesn't matter. So then we'll say this dot values dot or index equals this values parent, and then this dot values parent equals temp, and then kind of the recursion that you could think of it being like that is going to happen because we're going to say index equals parent. We're going to now, we've swapped them around, so that's now our new parent. The index is going to remain the same, because remember that the index is actually just this part, right? We can swap items around inside the array, but the indexes stay the same because we're referring to a point in the tree. So this point in the tree, after we've swapped these two things around, right, we have 0 here, then we're going to start comparing to its parent. So we're going to set its index to 0, or sorry, it's going to set its index to the parent, and then we'll put continue, and that's going to jump back to the top of the while loop. So you can see that if you were going to write this with recursion, for instance, like you would take this index parameter and bubble up, and we would just call bubble up at this point, right? We would return another call to bubble up, and we would set the parent as that index this time. It's also a valid way of doing it. That's fine. If we don't need to swap at any point during this whole process, then we're done. We've got the tree into a partially ordered state, and it's in a good place. We can successfully use it as a priority queue. So at that point, we're done. And that is the bubble up operation. So yeah, so we can actually try this out with a really simple setup. Conduct a little experiment with it. So let's just design an experiment quickly that's going to let us tell if that worked or not. What I'm going to do is, like, let's take these same values maybe not quite so many of them. Let's do like, let's take not a 5 here. Let's put a 32 and we'll have this be our tree, right? So we're going to insert these values, which are going to be like 1, 5, in order. They're going to be 1, 5, 10, 32, and 44. We're going to insert them in like a different order because that's going to make sense. So let's do like 32, 5, 10, do 32, 5, 44, 10, and 1. That's a good order because it's going to imply quite a lot of movement around. And let's just see how that is actually going to work out. So let's insert 32 first. It becomes the root node. We insert 5. We need to swap. So 5 becomes the root. 5 becomes like oversized. So then we end up in this state of the tree. So with 5 being the parent of 32, we insert 44. That goes successfully as the right child. 10 comes in. We naturally have to put it at like, you know, the next open position. So 10 comes down here. We start bubbling up. So we look at the parent. Do we need to swap? Yes, because lower numbers are higher priority. So we swap 5 and 10. We check if we need to swap again. We don't, because 10's bigger than 5. So we're good there. And then we come to insert this 1. That's going to come here as like the right child of 10. So we'll put that over there to signify it a bit better. Then we need to bubble up. Is 1 smaller than 10? Do we need to swap? Yes, we do. So we swap those two nodes around. Do we need to swap with 5? Yes, we do. So we swap those two nodes around. And then in the end, we should have this as our tree. And then what that means is that the final ordering that we should observe is 1, 5, 44, 32, and 10. That's what we should expect to see as like the final order. We're going to put this order of elements in, and we expect to observe this as the order of values. And if we pull them out, we should pull them out in, well, we can't pull them out yet because we haven't written the bubble down for remove, but we should at least observe this. So 32, 5, 44, 10, 1. Let's make a queue, priority queue, and you could put the generic part in here, but we can do inference on that because of the initial values that we will have. So our comparative function, take a, b, and do a minus b, and our initial values, well, that will be, now I need to remember what I just said, 32, 5, 44, 10, and 1, 32, 5, 44, 10, and 1, got that right, double check, yes. And then what we're doing is just putting a break. Well, I guess we could just do a console log of q.values. And this is why I made everything public right now, is so we can just do like introspection of the like the currently operating internal values. So we'll just run that. And what we see is, interestingly, 1, 5, 44, 32, and 10. And let's make sure, 1, 5, 44, 32, and 10. So that's perfect. And what you can also see is that our array expansion code also works correctly, because we have 5 items in the queue, and we have 3 empty items. Like there's 3 slots with nothing in them. And yeah, that is because we did this exponential doubling, and now we have 8 items in the queue total. So we could push 3 more before we need to do another resize. So as an added benefit, that also works correctly. Good stuff. All right, so now we need to do the bubble down procedure. So this is pretty similar. We also start off with an index, and we're going from the root of the tree, so the index always starts at 0. Again, you could do this as a recursion operation. I will again do it as a while loop. And here, just like in Bubble Up, the first thing we did was grab the parent. Here we need to grab the left and right child. So the way in which we do that is, well, let's go back to the visualization. We're here, right? And in the simple case for the root of the tree, grabbing the left and the right child is obviously just like +1 and +2. So that's super easy one. But it's obviously not the general rule. So let's imagine we're at this 5. Yeah, so let's actually get rid of those and put these in instead, because this is the actual representation that we should see. So let's say we're here at this 5 and we want to get its children, which are 32 and 10. Well, what we actually do is we multiply this by 2, so we get to 2 and then we add 1. That gives us the left child, and then if we multiply this index by 2, so we get 2 and then we add 2, that gives us the right child. And that is the relationship, right? It's kind of yeah, you can actually kind of reverse engineer that out of like the way that the parent relationship works. But again, I really think that's quite beautiful. So let's make a couple of little functions here for like left child, and give that node index be a number. And so the child index, the way we calculate that is, like I just said, it's the node index plus 1, or sorry, the node index multiplied by 1, sorry, plus 1. And what we need to do now, just like we needed to check if we were at the root node with the parent, we kind of need to do things in the opposite direction this time. We need to calculate the index and see if like that's within the bounds of our array. Because what you'll notice in the visualization is that if we were talking about 44, which is here, well, we would do this node index times 2 gives us 4 plus 1, and obviously we're outside of the bounds of our known array. Like, we know that we have 5 items, so if that index is like you know, greater than or equal to the current length, then we know we're out of bounds. So let's put an if statement in for that. If child is greater than or equal to this dot length, return null. Otherwise, we will return the child. And for the right child, same thing. The only real difference is that we add 2 instead of adding 1. So cool. I really think that's pretty beautiful. So we get our left here. It's going to be this dot left child from this index, and right, same thing. And yeah, so this is where the complexity comes in. It's a little bit more than before, and there is a tricky little kind of piece of code that's going on here. You can write it in a slightly less tricky way, but probably if you look at a lot of implementations, this is the way you'll see it written. Is we're going to kind of make like a candidate to swap with, like an index that we're going to do a swap with. So call that swap with. Could be called swap candidate. Yeah, let's call it swap candidate. And in the beginning, we set it to index. So the implication will be that if we go to swap and it says, do you want to swap with the index? Like, we'll know that we are done. We don't need to swap with anything. So first of all, if left is not null, and then we're going to do our comparison operation. So this comparator function, and again we'll do this dot values index, this dot values left, and yeah, I'm not going to use index here. I'm going to use the swap candidate, and obviously that's going to be index in the beginning, but I'm going to leave it as swap candidate for now. So let's again get ourselves into a situation where we're kind of aware of what we're looking at. Let's say like we took away 1 from our thing and we had to move 10 up to the root. So we're going to be comparing 10 with 5 and with 44. And first we're going to be comparing with 5. So let's let's go here, let's go back into node, and let's see, can I grab my AB implementation? So what did I say? We're going to have 10 and we're going to have 5. So in this case, we need to swap these two, and this one is greater than 0. So the comparison operation that we're checking for is greater than 0 in this case. So in that case, the swap candidate becomes left. Like we could swap with the left. But we're also going to check to see if we could swap with the right, if like it's kind of a better candidate. So we'll do this, swap with the right, and we're going to pass in the current swap candidate and the right. So if we were doing this, our swap candidate on the left here would be the 5, and like what's on the right hand side over here, we'd have 44. And obviously like 5 is a better candidate to swap with than 44, because it's like that's actually the lower value. So if we were to do this comparison, we would see that this one is negative. So we only want to change our candidate if this is positive, basically. If it's equal, then again, it doesn't matter which one we swap with, so we can swap with left. So we'll swap with right in that case. And then down here, we're going to check, like, is our swap candidate equal to the index? If it is, then we have basically exactly the same swapping operation to do again. So again, temporary variable. I'll make it the index just for being the simpler one. Then we can say this dot values at index is this dot values swap candidate. This dot values swap candidate is temp, and now we've swapped the two around. We're going to say that index equals the swap candidate. So no matter if we went to the left or the right branch, like we're going to continue in that direction. And then we'll do continue just like before to kind of do the recursion part. And to break the recursion, so we know when we're done, if like we didn't enter this if statement, like, and notice that we don't surpass this because of the continue, then in that case, we're done and we can return. So that is our bubble down. And yeah, if we've gotten that right, then this should actually be complete. And let's just have a think about a way to test that. The easiest way to test that is to do something that kind of just falls out of this data structure, which is to implement one final method in the kind of the public API called Heap Sort. Now what Heap Sort is basically you push a bunch of unordered stuff into your priority queue, and then you basically remove all the items, and the order you get them back is naturally just going to be your sorted data structure, sorted according to your priority. So we'll just return an array which has the length this.length, and then just for each element, in order to like generate each element, we'll run this function which just does this.remove, and that's going to give us the sorted array back. So that's going to be a really quick, easy test to see if if we've done this correctly, because what we'll actually see is a sorted version of this list. So let's see if that actually works. We'll run this, and it looks to me like we're getting stuck in an infinite loop. So let's see what I've done wrong here. When we do remove, if it's 0, we return null. We get the value. If the length is 1, we do this stuff, which is set length to 0. Grab that, set that to null, and return the node. So that should be fine. Otherwise, we set the node to the deepest element, we set the deepest element to null, we bump the length down, then we run bobble down, because we're removing something, we put it to the top, we bubble it down, then we return the node. So that looks pretty good. What I'm going to do is I'm just going to throw a breakpoint in, and we'll explore it. So we should have a length of like 5 at this point. So our root node is 1, that makes sense. We do the swap around. Let's go into the bubble down procedure. So, like visually, what's going to happen here is, and we were like this before, right? So we're going to pop this one off. 10's going to go in, and then we're going to be swapping with the left branch, and then we're going to be in a good state, right? Because we're going to be like this, and then we don't need to swap 10 and 32. But let's go and have a look and see what happens. We grab the left and the right. We should have something for both of those. We do. Set the swap candidate for ourselves, and we should enter this statement, right? And we do. And then we should go to do this on the right as well, and we shouldn't enter this one. So we skip that. That's good. Oh, this is the problem. Yeah. So you shouldn't be doing it if it's equal to the index, but if it's not equal to the index. So let's try the whole thing again, see if we escape, and we do. We get 1, 5, 10, 32, 44. We get a sorted list back. That looks like it's working correctly. And with that, that is actually the implementation. Let's quickly come in here and set a bunch of stuff to private. So those are private to our API. Insert, remove, and heap sort, they're all public methods. Parent, left child, right child, bubble up, and bubble down. They are all private. And yeah, that's pretty much it. Obviously, it would be good to write some true tests for this, but yeah, I'll leave that as an exercise for the viewer. Yeah, so I wanna extend my thanks to you for watching this video. If you're new to this channel, this is your first video that you've seen, then I would recommend going and taking a look at the back catalog. Normally we don't do just data structures and algorithms, but we do build a lot of really cool, interesting projects, especially stuff that you don't see covered a lot. If you're a returning viewer, thanks for being here. Thanks for sticking around to the end. And if you're a patron, an especially large set of thanks to you. I'll see you next time, where we're going to be jumping into some compression, actually making use of this priority queue in an interesting way. So yeah, looking forward to that. Have a great one, and I'll see you next time.